Hey everybody, in this video I'm going to give us a little breakdown of how working with f of g of x or compositions of functions is really a good tool to prepare us for the difference quotient and applying something called the limit definition of a derivative, which is one of the biggest things you do at the beginning of calculus. So I have this little picture set up for us, so let's dive into it. All right. First thing I want to talk about is slope. What is slope? What do we use slope for? Well, slope is what we use to find what we might also call a rate. Maybe more specifically, it's a rate of change. At what rate is something going to change, right? Miles per hour, feet per second, cups of water per day. Like, it could really be anything. Okay. So when we graph, and the way we're used to looking at our graphs is we have an independent variable that we put on our x-axis. That's also known as our input. And an independent variable is something that is sort of moving along and doing what it's got to be doing. And we're going to rely on looking at that independent variable to figure out the dependent variable. Well, how much is that going to cost? Well, it depends. It depends on how many units you purchase. How tall were you? Well, it depends. It depends on what age you're asking me about my height. How much does the taxi ride or Uber ride cost? Well, it depends on the length of the ride and if there's a surcharge for weather, whatever. So these things depend on that independent variable. And our dependent variable is also known as our output. It's what we get out of our equation. And we're also probably used to seeing most of our equations written as y equals blah, 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 right? Some sort of function of x, some equation with x in it, right? So that's what we're working with, okay? And that's another reason why that it's sort of set up the way it is, and that's our output and all that good stuff. Now, when we find the slope, maybe you think of slope as your rise over your run. Rise, how much something might be going up or possibly down, and our run, using an R word, going for that, what is it, alliteration? How much something is moving over or left to right. Now, if something is rising or going up and running or going to the right, we think of it as being positive. And if we have something perhaps going down and to the right, we would think of that as a negative rate of change. Now, the units that we use on rate of change are always going to be the units of the y, this unit on the y-axis, over the unit on the x-axis. And that should make sense because the way you do good old-fashioned slope formula in a linear equation is we would do y2 minus y1 over x2 minus x1, right? Now, whatever y is, it could be two different y values, whatever it is. I'm going to actually even line it up with, let's go ahead, and I'm going to line it up with the two dots, the one that's like the red dot and the purplish colored dot, right? So I got a y value somewhere about there, and I got another y value somewhere about there. And we can call this one y sub 2 and y sub 1, right? And maybe we call, for now, this x sub 1 and this guy x sub 2. Sub as in subscript, right? That would make the ordered pair or coordinate point of that point right there, x sub 1 comma y sub 1. And that would make the ordered pair or coordinate point of this one, x sub 2 comma y sub 2. So if I wanted to find the slope of this little red line that's cutting through right over there that I'm tracing over right now, if I wanted to find the slope of this line, that slope could relate to this curved graph underneath as being what we call an average rate of change, where you kind of check in at one point, you check in at another point, and you find maybe the change in distance or the change in time. So maybe you found you drove along the highway and you traveled 60 miles in 1 hour. So on average, you were driving 60 miles per hour, even though maybe you were driving 65, you were driving 50, 55 at different points, but on average, you're averaging a pace of 60 miles per hour. That's your average rate of change. So you use this slope formula that you've been seeing for years, right? But the thing is, there's a lot of variables and subscripts going on here, and what we want to do is actually simplify this with function notation. So what I'm going to do is just clean this up a little bit, and we're going to just rename these points to get us ready for calculus, okay? Now, okay. So we're still talking about slope, we're still talking about our rate of change and all that, okay? But we're going to look at our two x values as being what I have labeled here. The first x value is going to be x. Good, great, it's x. The second one is going to be x plus h, where h represents, as we see right here, the distance between my two x values. Now, very often, and honestly for myself more typically, I tend to use delta x for this. And delta, the capital Greek letter D, and lowercase delta looks something, I don't know, like sometimes like that. You know, it looks like a lowercase d actually. Delta, we should know, means the change in. So it's how much something changes. And that's why this guy's x plus h, because you're really adding a certain amount to the x to get the new x value. So this way we're not introducing x sub 1 and x sub 2. All we need is this one x value and the distance, and we can kind of define everything right now. All right. Now, if this graph, this curve, okay, it could be anything. This could be a part of a parabola, a cubic function, some other wild polynomial. This could be part of a rational function. This could be part of some trig graph. This could be anything, right? An exponential graph. It could be whatever you want. It could be the product, the sum of those things. And if I wanted to know in calculus the rate of change along a curve at a certain point, like this blue line that was over here, the way you get the slope or the rate of change of something that's curved is different than how we've gotten slope of lines, but it starts off the same way. And that's what we're going to be doing. We're going to find the slope first of this little line segment here, because we have 2 points, and that's great. And we're going to slowly modify things and do a little bit of tweaking here, an adjustment to change it into being the slope of the line cutting through the curve to being the slope at exactly 1 point along the curve. This line is called a tangent line. And whenever you have a line, the slope is constant. Just think of the equation y equals mx plus b. M and b are known to be what we call constants. They don't change. Once you define them, they're locked into what they are. X and y, letters usually chosen from the end of the alphabet, are what we call our variables, and by nature, they vary. So this constant m, it's kind of ideal because once you have a rate of change that's constant and not changing, well, that's great because I don't have to worry about it. So I have a curve, and the slope on the curve is changing. It is variable. It depends. What does the slope depend on? It depends on which x value you're analyzing the slope at. If I look at the slope over here, it's going to be much steeper than the slope over here. And then the slope down right here, well, that almost looks like a slope of 0. And the slope over here, well, that's a negative slope. So the slope along a curve is very different than the slope along a line, in the sense that that slope is variable, and we're going to use the slope of a tangent line because a line has a constant slope, and that will make our lives easier. So, you know, hang in there, we're getting there. Okay, now to find the slope of a line, we need 2 points. I started to name the 2 points for us. I have their x coordinates. The x coordinates are x and x plus h. What I'm going to name this curve is something very general, f of x. It could be anything, whatever we want. So what y value will correspond to the input or x value of x? Well, that y value would be, that's a little hidden back there. Let's write it somewhere else. That y value we can call then the f of x. It's the function at x. And then what about the y value to go with this red dot? Well, if the input is x plus h, then the output is the f of x plus h. All right. So whatever this y value, this x value down here ends up being, we plug it into our function to get the corresponding output or y value. Hopefully it's all making sense so far. So what does that make my ordered pairs? So just for cleaning up the space a little bit, I'm going to erase and just label the ordered pairs. Okay. So erasing the messiness, and we're going to label now the coordinate points. So this one is x comma f of x, and then this one, let's even, maybe we'll do a little color coding in a way. That guy right there is going to be x plus h comma the f of x plus h. Okay, great. So with this function being named f of x and the ordered pairs being defined as x comma f of x and x plus h comma f of x plus h, we now can use our regular basic slope formula to find the slope of the reddish little line segment, which we actually call a secant line. So we're going to find the slope of that secant line. A secant line cuts a graph at 2 points. All right. So what will that be? The change in y sub 2 minus y sub 1 is now f of x plus h minus f of x all over change in y, or change in x, which is x2 minus x1, is going to be x plus h minus x. Now, when I have the numerator, I can't do anything about that. I can't cross out f of x or anything like that. Like this guy and this guy, like they don't subtract from each other. You can't do anything about the fact that the one is f of x plus h, the other is f of x. They're not like terms. I can't combine, cross out, and anything like that. So they stay as they are. I leave them alone. However, in the denominator, I don't have anything put into a function, so I actually can clean it up, because this x right here minus x is going to leave me with just what in the denominator? It's going to leave me with just h, and that should make sense because h, or in other cases delta x, is in fact the change in x. Like that is exactly what should be in our denominator, right? So that right there is what we call the difference quotient. Now the name, when it comes to mathematicians, we are not creative. We name everything pretty much what it is. So a difference is the answer to a subtraction problem, and a quotient is the answer to a, well, division problem. So this is the, not a difference quotient, not just any ordinary one, but this is the difference quotient. All right, super, super important guy. Now, again, does that get me the slope of the blue line yet? Well, not yet. And that's what you want when you're in calculus. We really want that, not average rate of change, not slicing through a graph at 2 points, but we want that instantaneous rate of change. We want that slope at just 1 point. But if you only have 1 point, you can't find slope, because by definition, we need 2 points to find slope, right? Now, do you think that the slope of this red line seems really close to the slope of the blue line? I mean, it could be worse, but it could also be a lot better. What if I chose to make the h smaller and I picked a point a little bit closer to the purple point? Well, now my secant line might look a little bit more like that. Is that a little bit better? Is that closer to the slope of the blue line? I would say so. Well, what if I picked a point a little bit closer? Well, then it's going to be even closer and closer and closer to the slope of that blue line. So, in other words, the smaller h's, right? The smaller that we make the h value, the more precise the slope will be, the secant line will be, the more close it will be to being the slope of the tangent line, which is really what we want. I mean, in a wonderful, ideal world, we would want the distance, h, over here in between those two things. I mean, it'd be great if it equaled 0, right? If we can get that to equal just a little cute little 0, I mean, that would be wonderful. But can I put 0 in my denominator? Absolutely not. That would be undefined. So we can't actually get to 0. Well, can we get infinitely close to 0? Can we just keep plugging in smaller and smaller and smaller numbers, like 0.00001 as the distance between? What if we stuck some more zeros in there? If we did that, we would have to do that using something called, which we've been talking about in class, something called a limit. And a limit is a way for us to get really close to something without necessarily getting there. So by finding the limit as, and the limit is always asking us what happens to like the output value, as h, which is, we define it to be that distance between our two x values, which is going to be our denominators. If we find the limit as h doesn't equal 0, but does approach 0, and that's how we write it. If we find the limit as h approaches 0 of this big hot mess right here, f of x plus h minus f of x all over h, that will give us the slope of the tangent line. That will give us our instantaneous rate of change. That will give us the slope of the tangent line. That will give us the derivative. And the derivative, as you will learn, is a huge player in the world of calculus. So looking at the next videos that are on this playlist are a bunch of classic examples with tips, advice on how to actually apply this to those cases. And if you can apply it to those fundamental cases, you're on a really good trajectory to be successful. So hope this makes sense. Check out the next video. I hope this wasn't too long, but I really wanted to give a thorough breakdown because some of you might be in pre-calc now, algebra 2, calculus, who knows? And if you really don't have a strong understanding of this, well, that's not great. So I want to make sure you really are getting it, okay? So rewatch, ask questions. It's about, what, 17 and a half minutes? All right, that's not so bad. So if you did okay, throw me a thumbs up. Question, comment, concern, request, anything you want. Leave me a comment and we will take it from there. Bye for now. Adios.